Hey guys, so today we're going to be doing a little short lecture about Chapter 13, which covers more of this organic chemistry functional groups that we talked about in Chapter 12, but we'll be going a little bit more in depth in a few of them, those being alcohols, phenols, thiols, and ethers. And they're all very similar. In essence, they use, well, not thiols, but phenols, alcohols, and ethers are very similar as they have an oxygen in the functional group. So let's go through it rather quickly. This will probably take around 10 minutes. So the functional groups that we're going to talk about are alcohols, phenols, and thiols, right? So an alcohol, I mentioned in Chapter 12, it is just one of these organic chemistry groups, one of these hydrocarbons that has an OH group, one or more, attached to it. So one of the simplest, or the simplest alcohol is methanol, and that's very toxic for us to ingest. And it is a methane. Remember we talked about methane being CH4. I'm going to write down methane. I'll show you how similar they are. Why isn't my pen working? I don't know why my pen's not working. Okay, whatever. So you have methane, which is CH4. If you take off one of the hydrogens and you replace it with an OH group, that creates methanol. And phenol is a different functional group that also has an alcohol on it. It's very similar to an alkyl alcohol, or an alcohol. Phenol is a benzene ring. Remember we talked about that aromatic functional group, which has the alternating double bonds in a ring structure. And if you add an alcohol group to a benzene ring or an aromatic ring, it creates a phenol group. So this is a phenol group. Then you have a thiol group. So a thiol group is basically if you have any hydrocarbon chain with a sulfur and a hydrogen on it. Now I know I didn't mention sulfur as being one of the key organic elements. The ones I mentioned were carbon, hydrogen, oxygen, and nitrogen. But sulfur is a trace element that occurs in our body when comparing to the main four. So there's sulfur in our amino acids, in definitely our in cysteine. That's the amino acid that has sulfur in it. And there are also sulfur groups in other different types of structures, but it's not too common. But it is a biologically relevant group in our body, so it's important to mention. All right, so here they are in action. You have your alcohol, your phenol, and your thiol. And so for naming, the naming basically takes our simple naming that we talked about last class or last lecture in Chapter 12, where we went over methane being 1 carbon, ethane, or the prefix eth being 2 carbons, prop being 3, bute being 4, and then pent being 5, and then so forth. So it just follows that naming scheme, but instead of making ethane or ethene or ethine, right, we are going to be talking about adding a different ending of anol when we're talking about alcohols. So for methane, if you make methane into methanol by removing one of the hydrogens and adding an OH, like I mentioned before, what you will end up with is methanol. So you're basically changing the ending, the ANE, to ANOL. So that'd be methanol. Another name of it is methyl alcohol. But the official name, based on the international naming nomenclature for organic chemistry, is methanol. And the same thing for ethane. You see CH3CH3, that's what we talked about last class, as being an alkane with 2 carbons. And once you make it an alcohol, the ANE, again, changes to ANOL. And a common name for that is ethyl alcohol. So it's tough in chemistry when you're first learning. When, for example, when I was first getting into the laboratory, when I was in an undergrad, you see different labeled containers. Some of them say ethanol, some of them say ethyl alcohol. And I first had to remember, wait, is that the same thing? What do I do? That's why the international naming nomenclature is very important. So all the different chemical containers can be labeled in a normal way. Because a lot of these are very simple. There's only a couple names. But for other more complicated structures, there's multiple names that can be used. And it could get confusing once in a while. So ethanol is, like I mentioned in Chapter 12, is our alcoholic beverages are made from ethanol. And ethanol, it is toxic to us. That's why we get drunk. Drunk is a toxic reaction to an intoxicating agent. That's why you call it intoxication, because you're ingesting a toxic chemical. but it's in very small quantities. It's not going to kill you, but you know that people do die of alcohol poisoning, and you get your stomach pumped, or if you don't, you might die. So it's dangerous, and drink responsibly is what I'm trying to say. And it's created through alcoholic fermentation from different starches and sugars. Okay, so then you have a thiol. So thiol, you imagine sulfur. Maybe in common knowledge, you know, sulfur is analogous to a bad smell. Oh, it smells like a sulfur or whatever. It's just very, very potently bad smell. And different thiol groups are what is in skunk spray. So that's why skunk smells so bad. They have this trans-2-butene-1-thiol. So we'll talk about that naming in a minute, but basically, or we'll talk about it right now, actually. So this is a really good basic organic compound where you can actually look at the name and break it down to see which part of the name corresponds to which part of the structure. So let's look at in general. And I know this might be a little bit advanced if you haven't looked at organic chemistry in depth, but I'll just go through it. So trans-2-butene-1-thiol. So if you look at the trans, so this trans represents the three-dimensional representation of the chemical structure. And I'll explain that. It's usually over a double-bonded carbon. So what I mean by that, what trans means, is that one of the groups, so before I go into this, I should say that we ignore hydrogens. So singular hydrogens, such as this hydrogen on the top right and this hydrogen on the bottom left, they have to be there to complete the 4 bonds on carbon, like I mentioned last class. Remember, we assume all of the carbons have 4 bonds, and if they don't, we just stick in hydrogens there, and that is how it's represented. Or that's how it's actually bonded, and that's why we represent it that way. So for trans, that means the non-hydrogen groups are on the opposite sides of the double bond. So let's see the non-hydrogen groups. That's this CH3. First, locate double bond right here. CH3 is up here. And then the other group is this CH2SH. CH2SH. So CH2SH is on the bottom right side, on the bottom side of the double bond. Meanwhile, the CH3 is on the top side of the double bond. Therefore, they have a trans configuration. And this trans configuration is important only for double bonds and triple bonds. Well, really double bonds. And the reason why is because this double bond cannot rotate. Double bonds are held in a fixed conformation that the carbons cannot freely rotate around them. In a single bond, the carbons around a single bond can rotate, and this CH3 can totally be on the bottom, it could be on the top, depending on what time period you're holding it on. They're in a mixed conformation, and they can rotate freely. This double bond holds them in place, because if you imagine you're taking this as a stick structure, and you're holding this in your hand, and you try to twist it, you're going to interfere some resistance. You're going to have some resistance. And the reason why is because the electrons that are holding this double bond together, and if you imagine these as just like sticks, they're going to twist with each other, and there's really a limit to how far you can rotate it. So it's really not going to rotate at all, or it takes a lot of energy for it to rotate. So we can just assume that the carbon-carbon double bond does not really rotate. It's kind of held in place. So if that's the case, we can say there is a difference. There's a structural difference between a trans conformation, which means that one of the groups is on the top left and the other's on the bottom right, or one's on the top, one's on the bottom. Doesn't have to be right or left. And a cis conformation. So cis is the other conformation. And that occurs when you have, let's say this CH3 group was on the bottom left, and this group was also on the bottom right. Or they're both on the top. So cis means same, trans means the opposite sides of this double bond. So that's what that means. Now let's go to trans-2-butene. Okay. So butene, that looks familiar, right? So butane is when you have your alkane with 4 carbons in it. Butene is when you have an alkene with 4 carbons. So that means you have a double bond somewhere in the 4-carbon structure. So let's count. 1, 2, 3, 4. All right, there's our 4 carbons. There's our butene. You see the double bond in the middle here, so that's what makes it butene as opposed to butane. And the reason why it's 2-butene is because that double bond occurs at carbon number 2. So, and the thing is, you need to, so there's this nomenclature and there's names, or sorry, numbers with this nomenclature. And those numbers correspond to the number of carbon, so you could number all these carbons, starting from the carbon with the, well, how do I explain this? The substituents of the carbons need to have the lowest possible numbers. So I'll say that one more time. The substituents, meaning all of the branching points, meaning SH4 is the only branching point here, off of the carbon chain, needs to have the lowest number carbon that's possible. So for example, 1-thiol, that means this is carbon number 1, and it has a thiol group on it. Therefore, this is carbon 2, this is carbon 3, and this is carbon 4. So where does our double bond occur at to make it 2-butene? Our double bond occurs at carbon number 1, 2, right at 2, between 2 and 3. Because it's between 2 and 3, we can say that it occurs at carbon 2. So that's why we have 2-butene, and then 1-thiol is carbon number 1 has a thiol on it. So once you break it down like that, it doesn't seem too complicated. All right, here's some other ones. So let's look at, these are more thiols. Let's look at methane thiol. That's very simple. You just have methane with thiol on it. Then you have 1-propane thiol. Propane thiol. Propanethiol, however you want to call it. So the reason why it's 1 is because on the first carbon, see if you want to count from the lowest, here's a substituent, SH. If you want to count from the lowest number, so it would be carbon number 1, 2, and 3, on carbon number 1, it would be the thiol. So it would be 1-propane thiol because propane has 3 carbons, 1, 2, and 3. So that's the smell of onions. Then you have 2-propene 1-thiol, which is the smell of garlic. And that you have to name it in the same exact way. The carbon number 1 has a thiol, and then the rest of it's propene. It's 2-propene because in carbon number 1, 2, carbon number 2, that's when the double bond occurs. So you have to number the carbons in which the substituent occurs at the lowest number. So that's the key rule. Then you have, the last thing we're going to cover, we're almost done, is ethers. So ethers, they have an oxygen in the middle. So basically what this is if you have an alcohol group, just like we saw up here, and for methanol, if you have an alcohol group and you get rid of this hydrogen, and you replace this hydrogen with another functional group or another carbon chain or something different, you get an ether. So furane is an ether, otherwise known as isoflurane, and it is an anesthetic. So here's an example of that, and you can see, and these names, when they get a little bit complicated, they just make their own trade names for it. So isoflurane is that trade name. So here are some ethers, some common ethers that you can name, and this is methoxymethane, otherwise known as dimethyl ether or dimethyl ether. So there's different names. That's where it gets complicated. But let's look at dimethyl ether, dimethyl ether. You see an ether, and there's one methyl on each side. So a methane group is otherwise known as a methyl, and that's why it's called dimethyl ether. Methoxymethane, that's another name for it if you look at it in a little bit different way. So you can say, all right, this is my methane, methyl, methoxy, oxygen, methane. And you just kind of name it like that. So for this one, you would have ethyl. You did different ways to name it. So you can have methoxy group right here, and then ethane. Methoxyethane, you can have methoxypropane, methoxybutane, etc. And then also for the same structure, ethyl methyl ether. That's a mouthful. Methyl ethyl ether. So you have an ether, you have a methyl on one side right here, and you have an ethyl on the other side. Both of these names are completely correct, which is what makes organic chemistry tough to learn because there's so many different names, and sometimes they mean the same exact thing. So here's one with benzene. So looking at the structure, it could be methoxybenzene because you have a methoxy group right here, methyl oxy, and then attached to a benzene. Or it can be called methylphenyl ether. That's where it gets tough. So remember we talked about a phenol group before. So phenol, if you want to attach a phenol to something else, you would call it a phenyl group. So where are we at? So phenyl. So it would be a phenyl, which is this group with the benzene and the oxygen. And then all you would have to do is add a methyl to it. So it would be phenyl methyl ether. And you have to say ether because it is an ether. So I know that could get complicated, but it's just to get exposure to this before you go into Chem 2. So then you have alcohol. So the last thing we cover is classifying different alcohols. There are 3 types of alcohols. There are primary, secondary, and tertiary alcohols. And all that means is the number of carbons that the okay, so the alcohol is attached to a carbon, right? OH is attached to a carbon. That carbon that it's attached to, the number of carbons that it's attached to determines its primary, secondary, or tertiary structure. If you look at these pictures, the OH, the alcohol, is attached to 1 carbon. That 1 carbon, it's not how many it's attached to, because they're all attached to 1 carbon. They can't be attached to 2 carbons. But that carbon can be attached to 1, 2, or even 3 carbons. When that carbon is attached to 1 carbon, it is a primary alcohol. When that carbon is attached to 2 carbons, it is a secondary alcohol. And when that carbon is attached to 3 carbons, it is a tertiary alcohol. So let's do some practice. Classify each of the alcohols as primary, secondary, or tertiary. So let's look at the first one. You have your alcohol. Let's look at the carbon that it is attached to, this one. That carbon is attached to 1 carbon on the left and 1 carbon on the right. It doesn't count this carbon. It's only carbons that it is directly attached to. So it's 1 and then 2. Therefore, this would be a secondary alcohol. Let's look at B. CH3, CH2, CH2, OH. The O is attached to 1 carbon, of course. And then the carbon that it is attached to only 1 carbon. So it would be a primary alcohol. And then C, the OH, the alcohol, is attached to the carbon. This carbon is attached to 1, 2, and 3. Therefore, tertiary. So there we go. And that's it. So we kind of covered this in not that long of a time, probably 15 minutes. And that is it. So your final exams will be due on Friday night, and I will have the grades up by Saturday on CUNY 1st. This is for the spring 2020 semester, just in case other people will watch the video in the future. So good luck, stay safe, and good luck on the final, and let me know if you have any questions. All right, bye-bye.